Now we will continue our study on the proof, especially generalizing from the generic particular using the subjects of rational number. And again, just a quick reminder, when you do proof, it's always good to keep asking yourself, what does it take for the conclusion to be true? So now we will begin with introducing the definition of rational number. Many of you already know what it is, but here's the definition. A real number R is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. If R is not rational, then we call it is irrational. So the first task is always when you have a definition, usually it's in English sentence, try to rewrite it using quantifiers or convert it into symbolic form. So let's give a try. Again, pause the video if you want to give a try first. So here, R is rational if and only if. Okay, here's what we try to quantify. So as long as this number R can be expressed as a quotient of two integers, in other words, you really have to find two integers, right? So therefore, I'm going to say there exist two integers, A, B, and their integers in Z, such that, and you can write this as a quotient of these two integers where the denominator should not be 0. So I'm going to say where B is not 0. Okay, and then when you look at this definition, the symbolic form, what kind of action do you have to do to prove that a number R is a rational? So in other words, if you look at that, this is your task, right? You need to find, in other words, you need to search for or look for like A and B basically, so that R is equal to A over B. And by the way, A and B, they have to be integers. Okay, now let's use the following examples to get to know this definition very well. So now suppose I want you to identify negative 12. Is that a rational or irrational? And then you have to prove it, okay? You have to actually verify it is a rational or irrational. So first of all, negative 12 is actually rational because I can find two numbers, A and B, they're both integers, so that the ratio is equal to negative 12. There are many ways to do that. So some of you may say, hey, I can find two integers, one integer is 12, the other one integer is negative 1. Or some may say I can find two other integers, say the first one is say negative 24, the other one is 2. So do you see they're all equal to 12? There are infinitely many ways to do that, right? You can recognize that. So, but here, as long as you can find 2 so that the ratio is equal to negative 12, then it is. So therefore, my conclusion is yes. And this is my little short proof. I did not write that in a long and complete sentence, but here we try to get familiar with the definition. So I just gave it as short as possible. So what about 0? And again, pause the video anytime that you want. So I will say yes, because this is equal to 0 over 1, two integers. Or you can say 0 over negative 1, or any other way, right? So you just need to give one way. I'm just listing more than one as a demonstration. So this is yes. And the next one is yes, because this is equal to negative 7 over 5, two integers, ratio of two integers. Now, no, this is no, because according to the definition, the B cannot be 0, and this is actually undefined. So this is not a rational number. So this is actually undefined and not a rational number. And not irrational, by the way. It is just not a real number. Now 0.13, is this rational? Yes, because I can find two numbers. So again, try to think about two numbers that you can find so that the ratio is 0.13. And here it comes, 0.13 over 100, because there are two integers. You cannot argue, say this is equal to, you cannot say this is like 1.3 over 10. This won't count because 1.3 is not integer. So this won't constitute a proof. This is not a proof. So now this is yes. What about the repeating digits? Many of you already know from your prior knowledge, you know the repeating digits, repeating pattern is a rational number. Now, you cannot just say that here. To prove that it is, you actually have to find two integers, right? So that the ratio is this guy. And I can actually find it, and you can check 13 over 99. This is, if you use your calculator, you will see that this is it. Now the question is, how do you find it? There are a couple different ways to find it. One way is you can write this as 0.13 plus 0.0013 plus 0.000013 and so on and so forth. Basically, you break this number into a sum of infinitely many numbers, right? And you can see the pattern every time you have two extra decimals here. And then you can certainly you can think of this as like you can factor out 0.13, and then here you get 1 plus. If you factor out 0.13, then this is 0.0001, and the next one is 0.00001, and the next one will be two extra zeros. And now this actually is a geometric series because this multiply the previous by the common ratio. So here this is I'm gonna make a geometric series, and with common ratio r equals common ratio. Let me try not to use r because we are talking about r, using r for rational. So 0.001, that's the common ratio. And we do have a formula for that. Basically, if you have 1 plus a squared plus a cubed plus and so on and so forth, and then this is going to be 1 over 1 minus a, as long as the absolute value of a is less than 1, then this is the formula. Here the a actually is 0.01 in this case, so I can find it using 0.13 times 1 over 1 minus 0.001, which is 0.13 over 0.9. Oops, I think my ratio is actually a little bit off here. So actually this is 0.001, so 0.999, right? So 1, 2, 1, 2, 3. Actually, I'm sorry. That actually I made a little mistake here, a tiny mistake here. This is supposed to be 0.01 because there are 4 decimals here. Here I have 0.13. There are 2 decimals. This should be 2 decimals, not 3 decimals. So I have to make a little change here. So you might have to. So this is 0.0001, and so on and so forth. The common ratio is actually hundredth, not thousandth. 0.01. Okay. Sorry about that. That actually is supposed to be 1 less 0. Therefore, this is actually 0.99, 1 minus 0.01. So 13 over 99. Let's make sure that it is right. And okay, so I did check using my calculator. It is correct. Okay. So sorry about that. And now the second approach, I'm going to talk about second approach. Second approach can be, you can think of it as you can create an equation. So let me call this x as 0.1313 and so on and so forth, right? and so on and so forth, which is you can think of this as 0.13, and then you can think of this as sorry about that. Let me just, let's just begin with that. Now let's multiply both sides by 100 to both sides. So 100x equals 100 times 0.131313 and so on and so forth, right? And which means 100x equals, so when you multiply by 100, you just move the decimal twice to the right. So 13.131313 and so on and so forth. And do you see on the right hand side, you actually can break this as 13 plus 0.131313 and so on and so forth. I hope you recognize this is what we begin with. This is exactly your x. That's exactly what we begin with. Okay, that's your x. So that means this is the equation where x represents this number. So this equation is true. And let's solve for x. So subtract x to both sides, 99x equals 13. So therefore x is 13 over 99 by dividing both sides by 99, right? So therefore this is another approach to actually show you that I can rewrite 0.1, this number, the repeating decimal, into this fraction. So because they're both integer, therefore I can claim yes. All right, similarly, the very last one, this actually, if you see that this is repeating pattern, right? So therefore, just for the, you certainly have to find two integers so that this number is equal to the ratio of those two integers, and I'll leave this for you to try. And here's the answer. This is actually equal to 1340 divided by 999, and this will give this answer, so I can say yes. Now pause the video if you don't want me to spoil the answer for you, and to find the two integers that's the ratio is equal to this guy. Again, if I want to use this approach, I can rewrite this as, so I'm gonna, let me call x as 1.34, 134, 134, and so on and so forth. And I want to make sure that I see the repeating pattern. So you can try an error. I'm gonna multiply both sides by 1,000. Okay, 1,000x equals 1,000 times 1.34, 134, 134, and so on and so forth. Okay, and so on and so forth. Therefore, I have 1,000x equals, when multiplied by 1,000, I move the decimal 3 places to the right. So I have 1341, right? 0.34134, and so on and so forth. And now I'll break the right hand side into two numbers. One is 1340 plus 1.34, 134, and so on and so forth. And do you see why I do that? I try to recreate this guy, which is my x, right? So that's the trick. So whenever you have a new number, you try to multiply some number, and then you want to break this into, so you multiply by a multiple of 10 so that you can break the right hand side into two numbers. One is going to be the one you start with. So therefore I have, this is exactly x. That's exactly x. So now we have 1,000x equals 1340 plus x. And then when we solve for x, as x is going to be this. All right. So that's the first set of exercise. We use this exercise to make sure that you understand what it takes to prove a number is rational. So you really need to find two numbers, two integers, so that the ratio of these two integers is equal to that number. Then you successfully proved that the given number is a rational.